what I just indicated there, this idea of holding other variables constant, illustrates this whole concept of statistical control. And to understand statistical control is to understand one of the more important properties of regression analysis and why we use it. So why it's such a popular technique for data analysis. So when we talk about control, we talked about control in experiments with experimental control, and now statistical control has the same goal. The goal of this concept of control is to isolate causal impacts. So when we do data analysis, one of the more powerful conclusions we can arrive at from a data analysis is to delineate, to understand causal impacts. You know, we can see that these variables are correlated, but are they correlated because X is causing Y, or are they correlated for other reasons? This concept of a spurious correlation we talked about earlier. So causal analysis is what control is all about. And with regression analysis, as I indicated with that previous example, is that the partial slope coefficient, a partial slope coefficient for any of the predictor variables, shows you how much on average the response variable Y changes with the values of all the other predictor variables held constant, that is, controlled. And there's some Latin for this. You want a little Latin in your life, I'm sure. Ceteris paribus. And that means with other things the same, literally translated. So you'll see this phrase, ceteris paribus, in the regression literature. It indicates that we're holding the other predictor variables constant. And that then mimics the equivalence we attain with experimental control. It's not as powerful because with experimental control we do randomization and manipulation. And when we do that, we end up with equivalence of the groups, completely equivalent, except for any changes we manipulate in the groups. And therefore, if there's a difference in the response variable, we can attribute that difference to the change. But now, to assess the effect, for example, of a house selling price according to the size in square feet, we need to control for the age of the house. So if somebody asks the question, how much does this bigger house sell for compared to a smaller house? And you can't completely answer that question because there's other factors involved in establishing the market value of that house. And in addition to the size in the size of the house, another very important variable is the age of the house. You know, is it 150 years old or is it 2 years old? Salaries. So it's an important issue in each company faces, is the potential for discrimination on the basis of salary according to gender. And however, if you observe a difference in salaries between, say, men and women on average, it doesn't necessarily mean that there's overt discrimination going on in that company in terms of men and women, because there's other variables could also potentially explain the difference, such as the number of years that people have worked at the company. So if we want to conclude causality, we need to have some way of controlling potentially confounding variables. And it's this concept of a confounding variable that is why we need control, because when we control for confounding variables, we eliminate the potential impact of spurious relationships. So as indicated, experimental control with randomization and manipulation is always preferred, but it's not always possible. You can't manipulate gender, for example. You can't make somebody male or female for the purposes of a study. You can't manipulate the MBA program a student attends to understand if you're looking to see the potential salary differences in MBA programs, say after a year of graduation from the program. So there's many issues in life or situations in life where we have to rely upon statistical control. Now the reason why it's not quite as powerful as experimental control is because we don't necessarily have all the potential confounding variables identified and measured and put into the equation. If you can't measure, if you're not aware of it and or can't measure the potential confounding variable, and you can't put into the regression equation, and you can't explicitly statistically control for. But you can control for variables you think historically have been important, and if you can measure them, and then you make an attempt, such as a gender discrimination study. There would be an effort to measure how long each person has been in the company, and as a potential confounding variable. So it's multiple regression then is the technique we use to accomplish the statistical control. But to do that, we need two or more predictor variables, which is what, of course, makes multiple regression multiple. So you have to be also careful here, because there's a tendency to over-attribute causality, causal inferences, just because somebody did a regression analysis. And that can be a real problem at different times, because it looks like when you're working with an equation, you're working with a causal system. And it's not necessarily, unfortunately, not necessarily the case at all. And so if there is an equation there, you just give me an example here. Okay, need the next slide, yeah. When we enter a value of x into the equation, out comes a value of y. Actually, a y hat here would be the specific value that comes out. And then if we enter a different value of x into the equation, the regression model, out comes a different value of y. It looks like we're doing a manipulation, and we change the value of x, we get different values of the response variable from our model. Well, that's correct, but there's nothing causal about that per se. It could reflect a causality chain, a causal chain, or it may not reflect a causal chain. So the key concept here is that the mathematical manipulation by putting values into it for the predictor variables could, but not necessarily correspond to any kind of causal impacts in the real world. And so what we have then is that you have to realize that ultimately this regression model analysis is based on the correlations of the variables with each other, predictor variables with each other, and with the response variable. That is actually, we have the data, but that actual model comes from the correlations directly. And these correlations could be spurious. The fact that I entered the spurious correlations into an analysis doesn't automatically make things causal. So you have to be careful here. And maybe the best way to illustrate that is with an example. And let's look at the fire truck example we saw before in terms of working with spurious relationships in earlier material. So we end up then with, we saw that there's a correlation, a real correlation. If we really went out and collected the data or read the newspapers when there was big fires and collected the data that way, we would find that the number of fire trucks at a fire and the damage, the economic damage at a fire are correlated. The more fire trucks, the more damage in general. So what does that mean? We can take the correlation and we can take that data between the number of fire trucks and economic damage, calculate the correlation. It's non-zero. It's real. It's significant. But of course it's spurious because there's a common factor, the severity of the fire. The severity of the fire causes the economic damage. The severity of fire causes the fire trucks through a chain of events, causes the fire trucks to show up at the fire. So to show how just doing a regression analysis doesn't necessarily imply causality, we can take economic damage in fire trucks, 2 columns of data values, and we can run a regression analysis on one on the other. We pick one, fire trucks and economic damage on fire trucks, and we'll find that because the relationship is real, the correlation is real, I should say, the slope coefficient will be not shown to be larger than 0. It's not going to be 0. It's larger than 0. But it does not reflect a causal relationship. Instead, the slope coefficient is a useful way to describe the relationship between damage in fire trucks, but it isn't causal. It's interesting information. It tells us that, for example, if for each additional fire truck, we can figure out what the average amount of damage is, but again, obviously not causal. So let's pretend we actually had the real numbers for this and actually ran the regression analysis. What are we going to see? Let's say that we have the economic damage D in thousands of dollars, and we also have the number of fire trucks, and we're going to basically make economic damage the response variable, and fire trucks will make it be the predictor variable. And let's say we actually had the data. We don't, but let's say we did and came up with this regression equation. Right? The forecasted, the fitted value for the number of the economic damage is going to be 10 plus 85 times the number of fire trucks, where the economic damage is measured in thousands. So what does the slope coefficient of 85 mean? It means that on average, that for each additional fire truck, the amount of damage increases by $85,000. Again, it's true. It's not wrong to say that. It's just not a causal relationship. So we have a positive slope coefficient, but we're not trying to say the fire trucks cause the damage. In fact, it's the opposite. The presence of the fire trucks minimizes the damage. So it's complete opposite of what the actual reality is, but it's still a valid regression equation as long as you do not overinterpret it. And so what we need to do in regression analysis is put in a third variable, severity of the fire. And if you put in that third variable, severity of the fire, you will see that the effect of the number of fire trucks will disappear. So when this number of fire trucks by itself, it has a slope coefficient of 85. If you put in the severity of the fire, which then actually is the causal influence on the number of fire trucks, you'll see that the slope coefficient for the number of fire trucks will essentially vanish. It will disappear. It will be approximately equal to 0 and almost certainly not significant in terms of generalizing to the population. So the slope coefficient in the multiple regression controls for the effects of the other variables. So if we look at the slope coefficient for the number of fire trucks in a multiple regression equation where severity of fire is also present, we will see that when we hold the severity of fire constant, that is for the same level of severity of fire, then we end up with no impact at all on, no relationship, not even a correlation between the number of fire trucks and the economic damage caused by it. So regression analysis is our tool for causal analysis, but it's not necessarily always reflect a causal analysis. But as we put in more predictive variables, we get closer and closer to looking at the actual causal impacts. So we can say severity of fire impact upon the economic damage is much more of a causal impact, because when we control for the other variables, it still stays there.